Okie doke, so we're going to look here at from the 2012 AP exam, question number 1. And we see here we have a titration, so we got some lovely acid-base chemistry here. So hopefully you are excited about this because you're comfortable with it, right? Right. Okay, so first thing we see 1.22 gram sample of a monoprotic acid, HA, is dissolved in water. And the solution was then titrated with 0.25 molar sodium hydroxide. pH was measured, and the equivalence point was reached at 40 mils of sodium hydroxide. Very important. Equivalence point, 40 mils of NaOH has been added. And then here we have our data. Okay, so hopefully, bingo, you recognize sodium hydroxide is a strong base. The acid is monoprotic, so we have a 1-to-1 hydrogen to hydroxide or hydronium to hydroxide ratio. We don't know if this acid is weak or strong, and that's what question part A is asking. Explain how the data in the table above provide evidence that HA is a weak acid rather than strong. Remember our traditional hydrochloric sodium hydroxide titration, strong. Our equivalence point is always at 7 because we create water. Here, our equivalence point, you can see when it told us the 40 mils of sodium hydroxide is not at a pH of 7. Okay, 40 mils, pH of 8.62. So since the pH is above 7, we know that the acid is weaker than the base. But just to answer this question, you just need to point out to them at the equivalence point, the pH of the solution is not 7. At the equivalence point, the 40 mils of NaOH, you don't have to tell that because they tell us to us, but just wanted to put that there for you to see. And then you don't have to add which it would be if it was a strong acid, strong base titration. It would be enough just for you to tell them that you recognize that at the equivalence point, our pH is not 7. Now write the balanced net ionic equation. We're not looking for the balanced complete molecular equation. We're looking for the net ionic equation for the reaction that occurs when the solution of sodium hydroxide is added to a solution of HA. Okay, so again, net ionic, we are not going to include sodium, spectator ion. So we just have to show HA reacting with hydroxide, and the hydrogen goes over to hydroxide, so we get our conjugate base and we get water. All right, so again, net ionic, we're not including the sodium here. Calculate the number of moles of HA that were titrated. All right, so we are given information. We've got molarity of our base, 0.25 molar, and we know the equivalence point is 40. I don't know. There we go. So from that information, of course, at the equivalence point, the moles of base is equal to the moles of acid that we started with, that were titrated. So calculate the number of moles that were titrated. We had 40 milliliters, 0.4 liters, times the molarity of the sodium hydroxide, and it is a 1-to-1 mole ratio. So you can see that we ended up with 0.0100 moles of HA. And again, try and watch our sig figs. Zeros in front don't count, but we want to keep those 2 zeros so that we have 3 sig figs, because we had 40.0 milliliters and 0.250 molar. Again, you don't have to completely show the dimensional analysis. If you just showed, moles of acid equals moles of base, and then calculate the moles of base, that should be okay. Now calculate the molar mass of our acid HA. Well, we just found moles, and molar mass is grams per mole. So I wish we had grams. And if you look at the question again, the very first part of it says a 1.22 gram sample of our acid is given. And so right there, 1.22 grams divided by 0.01 moles, 122 grams per mole. Now again, if you were lost, flustered, whatever, and you could not find the moles of acid, but you're like, oh my gosh, I know molar mass is grams per mole, just go back and make a number up for part C. Put 5 moles, or 1 mole, or 0.5, whatever. Just make up a reasonable number. Don't put a billion or a million or a crazy number. Just put an answer there, and then you would just have to put whatever you put up there right here. So you'd go 1.22 divided by 5, give an answer, you would get that point because you properly used the calculated moles from part C to find the molar mass. All right, grab as many of those points as you can. And then there's this part, okay, the equation for the dissociation reaction. Now we know it's a weak acid. HA plus water makes hydronium and the conjugate base, and we're given a Ka value. So assume the initial concentration before any sodium hydroxide added is 0.2 molar. So our concentration of our HA is 0.2 molar, and we have our Ka value. Determine the pH of the initial solution. So remember our shortcut. Yes, there's an ice table involved, blah, 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 but when you get to the equilibrium part and the Ka expression, our Ka is equal to x squared over the concentration of the acid. And that x is hydronium, which is our link to pH. Again, if this was a base equation, they would give us Kb. Kb would be equal to x squared over the concentration of base, and our x would be hydroxide, which would link us to pH. But here we have Ka, so plug and chug. Ka and our concentration of our acid, 0.2 molar. So we get x equal to 3.5 times 10 to the negative 3 molar. Of course, you take the negative log of that to get pH, and we get 2.45, an answer that makes sense to us because it's a weak acid. So far, so good. And then here we have a big question, a really nice big question. This is 3 points, but you could do it. Calculate the value of hydronium in the solution after 30 mils of sodium hydroxide is added, and the total volume of solution is 80 milliliters. Okay. So 30 mils has been added, and that's why we see a question mark in our data table. We're not at the equivalence point yet. All right, at the equivalence point, at 40 milliliters, we just calculated that x is equal to 3.5 times 10 to the negative third molar. All right, so we should expect an answer less than that, right? Because now we haven't added the full amount of sodium hydroxide. Sorry, we should expect an answer less than that because this concentration was our hydronium at the start. So we have less than that because the neutralization reaction has begun. So hopefully this triggers in your head. We need an ice table. All right, and let's just look at this first part. Okay, so we have our reaction. The acid plus hydroxide makes the conjugate base and water. We don't need to involve water here. So the first thing we see is our moles before reaction, and that we calculated earlier. We have 0.01 moles of our hydrochloric acid, and before our reaction starts here, we have 0.00750 moles of hydroxide. Where the heck did I get that? Okay, and you can see it right over here. My moles of hydroxide, I know my molarity from above, 0.25 molar, and I've added 30 mils, so that's how I know that I've got 0.00750 moles of hydroxide. So we haven't hit the equivalence point yet, so 40 milliliters of sodium hydroxide is the equivalence point. So only adding 30, all of the hydroxide is going to be gone because it's been neutralizing. And that amount can be subtracted from our initial acid. So we subtract the 0.0075. And then that same amount has all been changed over into our conjugate base. So that's where those numbers are coming from. Okay, again, our moles of acid to begin with, the 0.01, we've calculated in part C. And then after the reaction, all of the hydroxides has reacted. Our weak acid is still in excess because we haven't hit the equivalence point, and our moles of hydroxide equals the moles of the conjugate base that has been made. I know, a biggin, but that's why these are AP exams and not just your regular exams. So once you see that, now you can calculate your concentrations, which we can then plug into Ka, which we can then find our concentration of hydronium. So our acid concentration is our 0.025 moles divided by 0.08, because our total volume is 80 milliliters. So that gives us that molarity. The concentration of our conjugate base is our 0.0075, again, divided by my 0.08 liters. I get that concentration. So now I know my acid concentration and my conjugate base concentration. I know my Ka, it was given to me before, so now I can solve for my hydronium concentration. So yes, technically in our expressions we would have the plus x and minus x, but again they're not going to make us do the quadratic, so you just kind of ignore them, and if you never write that on your test, it's no big deal. If you just have this part that you see down here, 6.3 equals this expression, you're totally fine. And when you solve away for that, you get the 2.1 times 10 to the negative fifth molar, again, which is smaller than my 3.5 times 10 to the negative third, because that was when we started. Okay. Big question, but again, your goal is to try and grab as many points as you can as possible. Not getting 10 out of 10 is not the end of the world by any stretch of the imagination. Grab as many of those points as you can. Hope this helps, and I'll see you soon.